So here we will see like two type of techniques that are used for digital circuit testing. So we will see these techniques. So the first one is functional testing and second one is fault modeling. Okay, so in the functional testing, as the name suggests, it is going for testing of the function. So whatever chip is there, whatever chip we have designed, we will go for testing with respect to the function. A chip is there and this chip is for okay. So by providing some input, we will be checking its output. So this is called functional testing, like we are verifying its truth table. If we are verifying its truth table, that will be coming out to be a functional testing. Okay, so it does not depend on the circuit design. So whatever circuit design is there, that we will not be checking whether what type of circuit they have used to design that particular chip. We will just go for testing its function. So here no detail of circuit design and layout are known, so we will not be having any detail regarding the circuit design, how the circuit has been designed, whether it has been designed by using CMOS technology or CMOS technology or PMOS or pseudo NMOS technology. Whatever technology we have used, that will not be available while testing the function, and also we will not be knowing the layout of. Okay, test only for correct output. So here we will be testing the chip only for the correct output. That means whatever input we are providing, with respect to that, whatever output is coming out to be there, we will be just testing. That is called functional testing. Another one is fault modeling. So here fault modeling is there. That means here we will be applying a series of test, or we call it test vectors. Test vectors are like test inputs, we will call it. We will be applying different test input or test vectors, or we call it test patterns. Okay, so test vectors we will be applying that will be formulated to check the possible faults which may occur within the circuit. So in fault modeling, whatever complete circuit complete IC is there, what type of faults could be there, we will be checking the fault, basically what type of fault it could be having, and that fault we will be checking with respect to applying different test vectors. We will be applying some test vectors, and these test vectors we will be giving some output. With respect to output, we will be checking whether this output is correct or not. If it is not correct, that means if this set of input we are providing 0 1, then what is the output, whether it is providing the correct output or not. If it is not providing the correct output, then what type of fault it could be there inside the circuit, that is governed by the fault modeling. So fault modeling basically specify the type of possible type of fault that could be there into the circuit. Okay, so there are different processes to find out the faults. Okay, so fault could be occurring at the time of manufacturing also. Okay, it could be the fault that have occurred at the manufacturing. So that could be with respect to the physical fault while depositing different layers or whatever methods we are using. Okay, now whatever faults have been occurred at the manufacturing time, and now we will compute the output with and without fault. So we have just considered like we have got fault. So what we will do is we will compute the output. We will compute the output for all possible input patterns, okay, or even the limited number of input patterns also, and we will be checking the output. Okay, so this output could be correct also, or it could be incorrect also. So we will be checking the output with the fault and without fault. Okay, now if no chosen set of faults detected, then the chip is fault free. So we will be checking the output with faults and without faults. So that means we will be providing some inputs that will be including the faults also, and that some without fault outputs and with fault outputs will be considered. And if at the end we have got the output that are showing no fault into the chip, that means it is a fault free chip. Okay, so in the fault modeling we will be going through these. We will be considering first faulty some faults that occurred at the time of manufacturing. Now we will check the output without fault and with the fault, and then if there is no fault, that means it is free from any fault and it is a correct chip that can be go for production. So fault modeling relies on type of faults considered. So there are basically we will be considering two type of faults. Okay, or basically we will be considering the logical faults. Okay, so in that logical faults, uh, stuck at faults are basically will be considered, and these stuck at faults are the faults that will be occurring at particular node that will be making that particular node either 0 or 1. So we have seen the faults can be stuck at 0 fault or stuck at 1 fault. So if it is stuck at 0 fault, that particular node will always be having a 0 value. If it is stuck at 1 fault, it will be having always 1 value. And another is bridging fault. So basically these two type of faults can be considered basically. So in bridging fault, adjacent nodes are sorted together, so there will be a bridge. So two nodes are there into a circuit, so these two nodes get connected, so it will be coming out to be a bridging fault. Okay, so we will see stuck at fault and bridging fault. So the advantage of fault modeling is with respect to the functional testing. So in the functional testing, we are just testing the function, whether it is giving particular output at given particular input or not. Okay, so we are not going for checking the faults. So in the fault modeling, we will be having a test in which a small set of tests is required to test the circuit. So a test set of test data will be required in case of fault modeling. But in case of functional testing, we will be checking all the functions with respect to all the possible input combinations. But in case of fault modeling, we will be providing a small set of tests. That means out of exhaustive inputs, we will be providing only a limited number of inputs, or number in test inputs we call it. So limited test inputs will be providing in fault modeling, and exhaustive inputs will be provided in case of functional testing. Okay, so in functional testing we will be testing the function for all the conditions, all the input conditions. Okay, so at the same time, it is not necessary that the digital circuits which poses all the fault modeling will be fully functional. So from there we can see, like, if uh, any circuit is there by using any digital circuit is there, if we have performed any fault modeling to that digital circuit, it does not mean that it will not be having any faults. Okay, so fault modeling will not be the method or the testing method that will be including all the faults, if we have, because we are using only limited number of inputs. It says, like, if we are going for fault modeling, it will not include all the possible faults. Okay, it will, if any circuit is there that has passed the test by using fault modeling, it does not mean like it will not be having any future faults. Okay, because in the fault modeling we are only using limited number of test inputs. We are not using all the possible exhaustive inputs. Okay, so that's why, because we are using a small set of test inputs. That's why it is like fault modeling will not be a fully functional, will not be providing a fully functional pass, we can say. But here it is saying like the probability of this will be very small. So there will be very small probability, like once you have passed a chip or any circuit through fault modeling test, then it will be having some error. It is having a very less probability of this. There are two terms, that is controllability and observability. These two terms will be used in basically in case of digital testing, digital circuit testing. Okay, so these terms will be were defined with an attempt to quantify the ease of testing a digital. So whether we can test a digital circuit or not, that will be governed by these two terms, controllability and observability. So for a particular digital circuit, whatever digital circuit is given, we will be finding whether it is observability, it is showing observability property or not, or it is having the controllability property or not. So one by one we will be seeing like what is controllability and what is observability. Okay, so controllability, so as the name suggests, controllability, it is a measure of how easily any node in the circuit can be controlled. So suppose any circuit is there, suppose any circuit is this one. Okay, suppose this is a circuit, A, B and C, three inputs are there, D, E and F. Okay, so this is one node, 2, 3, 4, 5, 6. Here different nodes into the circuit. Okay, so different nodes are there. So if particular node is we are able to, a designer is able to control the value at this particular nodes, then these nodes will be considered controllable, or we can say this complete circuit will be considered to be controllable, so that these controllability will be observed with respect to the basic inputs, primary inputs, whatever primary inputs are there. So here primary inputs are ABC. So if we are able to control all the possible nodes of this circuit by using ABC, then this circuit will be considered as controllable. That means it is showing controllability property. Okay, so controllability will be the property of any circuit in which the primary inputs will be able to control all the node voltages or all the node values. Then the circuit will be considered a controllable circuit, or it will be showing a controllability property. Okay, similarly it is observability. So observability means we are going to observe. So observe means observe is done to at the output. So whatever output is there, we will be observing the output. So at the output, okay, so it is like it is the measure of how easily the state of any node can be determined through primary outputs. So with respect to the primary outputs, how the particular node of this circuit can be observed, or we can say we can find. If we are able to find like what should be the value of D with respect to the output, suppose output is 0, then if we are able to predict like if output is 0, then D should be what value, either 0 or 1. If we are able to predict this value, then we can say like this circuit is observable. Okay, so these are the terms we should be using in the next few slides. Okay, so we will see controllability. Okay, so here, so suppose example circuit is there. Okay, so here we can say the inputs here E, F and G, three primary inputs are there. So this will be different complete circuit is there. Out of this we are including only F, E, F and G. So three primary inputs are here basically. So we can say these primary inputs, whatever primary input values will be there, that will be directly controlling the nodes 1, 2. Okay, So 1, 2, and 3. So 1, 2, 3 nodes, because this is 1, this is 2, and this is 3 node. So 1, 2, 3 is directly connected to this primary inputs. That means the node 1, 2, 3 is controlled directly. So we can say the 1, 2, 3 is directly controllable. Okay. And also here to trace node 5, 7, 7, 5, and 6, 7, 5, and 6 through primary inputs, we can see like if we want to control the nodes 5, 6, and 7, we should be having these three values. Okay, so these three values should be such that we should be able to control this. So in case of suppose node 7, here in the example we are checking at node 7, like what should be the value of node 7, or can we control this node 7 with respect to these inputs. So in the case we can see like here we can say like if we want to control the node 7 voltage or value, so here we are providing EFG. So if we are providing EFG equals to initially 0, 1, 1. So if we will be providing E is equals to 0, F is equals to 1, and G equals to 1. So 7 will be node 7 voltage will be coming out to be 1. Okay. Similarly, if we want to apply another output, input, primary input, that is this one. Okay. So 1, 1, 1. So here we can see like if these two test inputs are we are applying, then these two test inputs are able to control the value of node 7. Okay, either it is 0 or 1. So based on that, we can see like if we want to control any node that is very far away from the input primary inputs, that will be difficult to control. Okay, so here it is saying like if the node is closer to, this is primary input, if these nodes are closer to your primary inputs, it is very easily controllable. Okay, once we will be changing the E value, it will be changing. If we will be changing F value, 2 and 3 will be directly changing. So these are more controllable. So the nodes that are closer to primary inputs are more controllable, and the nodes that are very far away, these are away from the primary nodes, then it will be less controllable. Okay, so this is how the controllability can be defined for a particular circuit. Okay, so here another circuit is there. So sometimes it is not possible to control a node in the circuit through primary input. So there may be a condition like we will not be able to control a particular node voltage with respect to the primary inputs. Okay, so this is one circuit, circuit 1, this is circuit 2, and it is having the output, particular output. Okay, and it is going through another block that is called equality checker. Okay, so this equality checker will be checking whether these two circuits, okay, these two circuits are having the same value or not. Okay, so here the output from the two subcircuits is always same, because this is subcircuit 1 and this is the copy of, this is just a copy of the first subcircuit 2. Okay, so A and B are almost the same circuit, and these are having connected to primary inputs. Okay, so these are primary inputs. So primary inputs are connected and we are getting the output. So these inputs can have the same value with respect to particular input, the output will be same, but we can say like no way to influence output through primary input. So here whatever inputs are there, this will not be affecting the final output. There may be uh, a different circuit, or a circuit that is having a very far away point. So there may be a relation between input and output, like the inputs are unable to affect the output voltages or output levels. Okay, so to control a node, additional circuitry is needed. So in this case, we should be requiring an additional circuit to control these. So there will be some extra circuitry. Okay, and this circuitry will be this equality checker, whether it is equal or so this input is coming to the equality checker, and this is giving out the output. So here we are unable to control the output of this circuit. So these two should be equal. So this is coming to another block, and this is providing you the output. Okay, so this output will not be directly controllable by the PI. So we should be requiring some extra circuitry to get a control to particular node. Okay, so if a particular node is controllable from the primary inputs, it will be very easy to check for testing. For the testing purpose, we will be able to check whether it should be 0 or 1, or with respect to our desired sequence, we can make it either 0 or 1. So controllability is important for checking whether particular circuit can be tested easily or not. Okay, so if it is not directly connected, it will not be having a controllable property. Okay, so this node will not be controllable from the inputs. So that's why we will be requiring some extra circuitry to make it controllable. Okay. So that controllability can be having to have extra circuitry, we should require like these nodes we can control. This is a sub-circuit, this is sub-circuit. This can be controlled by primary inputs. So what we can do is to test this output with respect to input. What we can do is here an extra circuitry has been used. So this circuitry will be providing test mode signal. So if we are going for testing, it will be activated, otherwise it will be deactivated. Okay, so it will be activating whenever there will be a testing is there. If there is no testing, this will be deactivated. Okay, so this is how an extra circuitry is required to change the value of this node, because this node was uncontrollable in the previous slide. So now once we have introduced the extra circuit, this circuit will be activated whenever whenever we are having this node change. We need a node change of this node, then we will be requiring this extra circuitry. Because why we are requiring this controllability at all nodes? Because while testing this complete circuit, it will be easy to predict the value or provide this node with some particular voltage, and this will be testing uh, the complete circuit whether it is working perfectly or not. So for testing purpose, we may have another extra circuitry that should be used for testing. Okay, so now once we have used extra circuitry, this node can be considered like it have uh, a controllable node from the input, because it is having a test mode, and this will be providing you to direct this input. With respect to that, it can control the output. So controllability of sequential circuits is very difficult. So in case of a logical circuit, there is no feedback, so it will be easy to control. But in case of sequential circuit, it is very difficult, because large number of test vectors are required to change the value of a node. So in this case, large number of test vectors are required, like to in the sequential circuits, we will be requiring suppose whatever 00 input we have provided, so whatever sequence value is there, suppose it is a counter. So to have the output at different nodes, we should be changing this input pattern, so that with respect to that only the output will be changing. So and also this output will be having a feedback. Okay, so this feedback may be making this output uh, same, or we can say whatever desired output we are requiring, that maybe like it is not providing that. So in that case, a large set of test vectors are required to its value. So we should be taking care of that. So another problem is due to certain states of circuit never used. So also in case of sequential circuits, here like BCD numbers here, instead of 16 possible possible combinations of bits, we are only using 10 states. Okay, so here the remaining states will be causing problem, or remain if we are providing remaining state as the input, it will not be providing any output. So in that case, we are having limited number of test vectors. So these are the vectors where if we are providing a random input, it will not be correctly checking the faults into the circuit. Okay, thus these blocks are partitioned into a smaller blocks partition. So for this type of testing, we will be testing this type of blocks by breaking it into smaller parts. So once we will be breaking it into smaller part, less number of test vectors will be required for a particular test, and that will be efficiently uh, considering all the possible faults, and we can test it easily. Okay, so observability. So here observability is like if we are observing the output, so can we observe or check the value of particular node from the output? This is your observable. Okay, so here suppose we want to observe node 2. Okay, if we want to observe node 2, so node 2 is this one. So one has to see how logic is propagated into Z. So because observability is done at the output, output will be deciding the particular node. If output is 0, this particular node will be what can it this particular node is directly affecting the output or not. We will be checking it. Okay, so for that we will be finding out the path from this node to here. So in that case, we see if 2 nodes are there, this 3 is controlled by 2. That means 2 can propagate to here. Okay, but from here it can propagate through these 2. So 2 can propagate through 5, but it may be like 4 can cause the value change of these 2. So there may be like this 4 will not be making this 3 propagate through here. So if it is this, suppose this is AND gate, so this 4 node is 0, then whatever value is this, it will always be 0. So that means this 4 will be deciding the output at here. Okay, so this 4 will be deciding the output. Similarly, this whatever output is there, this 6 will be deciding here. In case of here, if it is NOR gate A plus B bar. Okay, so to have value, so suppose A is 0. Okay, A is 0, so B bar will be the output for A is equals to 0. But if A is 1, then whatever value of B is there, the output will always be 0. Okay, so here in this case, if this 6 node is 1, then this 5 is not observable at node 7 or at the output. Okay, so here to observe node 2, one has to set primary nodes 1, 4 and 6 such that the output depends only on the node 2. So that means if we want to observe node 2 at the output, that means 2 should be directly affecting the output. If node 1, 4 and 6 are going to affect this output, then it will be very difficult to detect the effect of node 2. Okay. Similarly, this process sometimes called sensitizing. So if we are making this 2 node to affect directly to the Z, this is called sensitizing the path, sensitizing the input, or sensitizing this node to the output. This is called sensitizing, or we call it forward propagating, or we call it driving the path from the node to the observable point or observable output. So this is different names that can be given to it, like we are either sensitizing this node 2 to output, or we are forward propagating it. Okay, so forward propagating it, and or we call it we are driving the path to the output observable output node. Okay, So this 2 can be observable here is like this should be node 1 should be 1 and this should be 1 and this should be a 0. 6 nodes should be 0, then only this should be propagating to this 2 will be propagating to Z. Okay, so this is how we should be checking whether a particular node is able to add the output or not. We should be considering the relation between observability and controllability. So here, so suppose this is, so controllability is observed at the input pins or the primary inputs, and observability is considered at the primary output. Okay, so at the primary outputs, observability will be high. Okay, this is ease of observability. Ease of observability means whether it is difficult or not. It is easy to observe at the output pins. If any node is there that is closer to output pin, it will be easy to observe. Similarly, if any node is there that is closer to input pins, it will be easy to control. As we are moving away from the inputs or as we are moving away from the output, okay, so if we are moving away from the inputs, the controllability of of a particular node will be keep on decreasing, and it will be very lesser. It will be small at the output pins. Similarly, your observability will be keep on decreasing as we are moving away from the output node. If we are moving away from the output node, it will be decreasing. Okay, so this is the basic of controllability and observability terms, like how it is related to other testing. Okay, so next in the next class we will be seeing the next topic, and one and two more topics are left. Okay, so we will see that into the next class.